Okay, so good morning, students, and welcome to today's class. So, we will be continuing with work power energy today. And in the last lecture of work energy, we had discussed about the work kinetic energy theorem, wherein we saw that the net work done by all the forces on a body equals to the change in its kinetic energy. And prior to that, we had also seen the calculation of work done by integration in the case of variable force, and in particular, the formula for work done by a spring. So we will continue from that point today, but we'll start with a very important definition within work energy, and that is the definition of conservative and non-conservative forces. So let's understand this further. So this is work, power and energy session number 3 for us. Okay, so the important couple of things that we saw in the last lecture. One was that work done by a variable force, or the general definition of work done. That is integration of force over path f dot ds from initial to final. Okay. Of course, in this we saw that if force is constant, then this path integration itself becomes forces dot product with displacement. So that we already understood before. Okay, we saw work done by spring force as minus half k into final position square minus initial position square. It's another special case of work done that we saw. So this was one of the things. Then the next thing we had seen was the work kinetic energy theorem, wherein we saw that the net work done by a body, I mean by the net work done on a body by all the forces acting on it equals to the change in kinetic energy. Okay. So net work done was summation of work done by all the forces, and change in kinetic energy was half m into final speed square minus initial speed square. Okay. So these were some of the aspects that we saw in the last lecture. Okay. Now today we will start with one important definition: conservative and non-conservative forces. Okay. So let's start by understanding conservative forces. So we've seen that in general, the work done by a force is defined as the path integration of force over displacement, okay, or the path integration of force from the initial to the final position. However, in certain cases, the force is such that when we do this path integration, the final quantity that we get, that is independent of the path taken. It only depends on the displacement. Very easy example of that is a constant force. The integration of f dot ds over a path becomes f dot s if the force happens to be constant. So ultimately, it does not depend on the path. It depends only on the displacement, or it depends on the initial position and the final position, and is independent of what path we take. Another example of this is spring force. And if you see the F dot D is integration for the spring force. Ultimately, it is such an expression that it only depends on the final position of the spring and the initial position of the spring. It does not depend on the path. So when this kind of situation happens, the force is called a conservative force. Okay. So the definition of conservative force is that they are forces. So if the work done by the force is independent of the path, okay, from initial to final position, okay, and depends only on the positions, that is initial and final, then the force is defined as a conservative force. Another thing is, for such a force, if we take the body on, or if the force is acting over what is called a round trip, that means we are coming back to the same position from where we started, then the net work done has to be zero. So for a conservative force, the work done in a round trip, okay, round trip doesn't necessarily mean a circular path. It can be any kind of path, but it should come back to where the body started from. So the initial position should be equal to the final position. Okay. So the work done in a round trip must be zero. Okay. So basically a round trip here is defined as a path such that the final position is same as the initial position. So in such a path, the net work done should be zero. So just note down this definition and we'll understand some examples of conservative forces. For conservative force here, the work done in a round trip will be zero only for conservative forces. A non-conservative force, we will come to that definition, can do non-zero work in a round trip. Okay, so first of all, what we can understand here is that any constant force is conservative. Okay, because Work done by a by a constant force, we've already seen, is F dot S. Okay. So here you can see that this final expression is path independent, and F dot S must be equal to 0 for the net displacement being 0, that is a round trip. So any and every constant force by definition is conservative. Example being the gravitational force at the surface of Earth. It's a constant force. Magnitude and direction are fixed. So for example, the weight of a body at Earth's surface is a constant force. It is like this. It is minus mg j cap. We take x and y axis like this. Okay. So therefore now if a body is, okay, sliding down from this initial position, let's say A, to this final position, let's say B. So while it is sliding down, mg is continuously acting like this. So what happens here is that the work done is independent of the path. It only depends on this displacement and this mg. And if this angle is theta, so the work done is, so that is mgs cos theta. In fact, that becomes mgh, where h is the height difference between these 2 points. So you can see it is independent of the path. It only depends on initial position and final position. If I had taken it from A to B via some other path, okay, even then the work done would have been the same. It only depends on initial position and final position. The same body now, instead of this path from A to B, suppose I had taken it by some other path like this, even then the work done would have been the same. As long as the displacement is the same from initial to final position. So as long as this h is same, okay, work done by gravity in any round trip will be zero. Okay, students, so hope you are clear with this point that, okay, Yasmith, what is happening here is, see, mg is a constant force, na? So work done by mg कैसे निकलता है? By the dot product of mg and displacement. So that in this example is mgh. Now, does the value of mgh depend on the path, or does it depend only on the position A and B? So for that, I've shown you the example. There are two different paths. This is path 1, this is path 2 between A and B. You can see there are different paths. The slope is different. You can have a third path also, like a straight inclined plane between A and B. But in all of these paths, the work done by gravity will be the same as long as the points A and B are the same. Now, the work done by gravity will be mgh, whether we are taking diagram 1, 2 or 3. Why? Because the work done by gravity is a path independent quantity. It is dot product of force and displacement. So it does not depend on path, it only depends on displacement. Is it clear now, Yasmith? Okay. So while all constant forces are conservative, okay, but it need not be that every conservative force has to be constant. Okay, there are variable forces also which can be conservative. So example, so conservative forces. So the definition being that the work done is path independent. Okay. Or a stronger way to check this is that the work done in a round trip must be zero. Now another example of this. No, Samarth, we cannot say that. We will come to the definition of potential energy later. Okay. So another example of this is spring force. We've seen work done by a spring. When we do this integration, it comes out to be minus of kx dx integrated from initial position to final position. So the work done has a formula like this. Now we can see in the formula the dependence of work done is only with the position, not with the path. So this is path independent. Okay. Depends only on x initial and x final, that is positions. Okay. And the work done by a spring is equal to 0 if the final position is equal to the initial position, that is in a round trip. So that shows that spring force is conservative in nature. Okay, so this is also another important example of conservative force. Just make a note of this, people. So while all constant forces are conservative, but every force which is conservative need not be constant. There are examples of variable forces which are conservative also, and one example of that is the spring force. Okay, now next up, we will look at one very interesting and important example of a variable force in a two-dimensional plane and how to demonstrate that such a force may or may not be conservative. So in this example, a particle moving in the xy plane, okay, is acted upon by a variable force given by the equation F is equal to, let's say it is 4 plus x I cap plus 2y square j cap, okay, where xy is the position, instantaneous position, so the force is in meters, sorry, in newtons for the coordinates given in meters. Now what is happening here is that our particular particle is initially at the origin of the coordinate system and moves from the origin to this particular point here, which has coordinates, let's say 2 comma 1 in meters. Okay, now in one case we will assume that the particle moves from the origin to the point P by this path that I'm showing. First it goes along the x-axis and then it moves along the y-axis and reaches here. So this will be what we'll take as path 1. Okay, and we'll also analyze what happens instead of taking this path. If the particle takes a path wherein it first moves from the origin along the y-axis to a point here and then moves parallel to the x-axis till it reaches the point P. So we'll analyze what happens in these two separate paths in terms of the work done by the force acting on the particle. So first of all, so if this particle moves from O, the origin, to the point P, okay, find the work done by the force F on the particle for path 1, for path 2, okay, and show that work done will be identical for any path from O to P, and therefore F is conservative. So let's understand this question in detail. So make a note of the question first, then I'll explain how to work this out. So x and y coordinates are given in meters over here. Okay, so let us understand how to deal with this kind of situation. Okay, so this is our diagram and this is the expression for force. So we'll need these two. So now let us actually calculate the path integration and work done by path integration for the first path. Okay. So the part 1 of the question, the work done by the force F for path 1. Okay. So this work done we can write as work done if I label this in between point here. If I label this in between point as A, so this one's coordinates will be 2 comma 0. Okay. So this overall thing is my path 1. So for during this path 1 I can say that the work done, because I'm going from O to A and then from A to P. So it is this kind of path. So I can divide it into two things, work done from O to A plus work done from A to P. Okay. Now for work done from O to A, that is the displacement along the line OA. So at any point in between, like let's say a point over here, the coordinates of the points will be x comma 0. Okay, with x being greater than 0 but less than 2. Okay, what will be the force? The y coordinate is 0, so the force will be 4 plus x I cap only. Okay, so the force acting at this point of time will be just a horizontal force which is variable like this. And obviously the displacement is along the x-axis, so that will also be like this. Okay, so when you are at that particular point, your displacement is just having an x component because you're moving along the line OA. So work done from O to A, nothing but this f dot ds integrated from the point O to the point A. So when you take this dot product, you can see you just have 4 plus x dx integrated from x equal to 0 to x equal to 2. So that becomes 4x plus x square by 2 integrated from 0 to 2. So the work done during this section of the path becomes how much? 8 plus 2. So it becomes plus 10 joules. That is the work done from O to A. So just make a note of this section first, then we'll discuss how to calculate the work done in the second part of the path, that is from A to P. Okay, now in the same thing, when we are looking at the work done going from A to P, looking at this part of the path. So now for work done from A to P, so displacement along EP. So an arbitrary point between A and P would be like this, that it would have a fixed x coordinate of 2 but a y coordinate like this. So at any point 2 comma y, where y is now increasing from 0 to 1. Okay, you can see over here the force will become what? Now the force will have both the components. It is 2 plus x square. Sorry, it is 4 plus x. So that is 6 I cap because x coordinate is fixed, plus 2y square j cap. So the force is now variable and also variable in terms of direction. So at different points we'll have different kind of forces. We'll have like this. The force will vary and its y coordinate is varying. So y component is varying, whereas the displacement is like this. It's along the y axis. So that is like this. Okay. So from this, if we calculate the work done from A to P, so now we can see the dot product of this force and this displacement will give us integration of 2y square dy, product of the y components, from A where the y coordinate is 0 to P where the y coordinate is 1. Okay. So this becomes 2y cube by 3 from 0 to 1. So that is 1 by 3, sorry, 2 by 3. Okay. Joules. Okay, so the work done from A to P becomes 2 by 3 or approximately 0.67 joules. So now we can see that the work done in path 1 was the sum of work done for this plus this, so that becomes plus 10.67 joules. Okay, so this process that we have done for the first path, now I want you to repeat that for the second path. Okay, so the second path you can again divide into two sections. One is the section along the y-axis and then the section parallel to the x-axis, and calculate the work done. Now when you do that calculation, interestingly again the net work done will come out to be the same because it happens to be a conservative force, but you have to actually have to do the calculation and show that. Okay, so take this down and use the similar method for the work done in the second path. Here we are completing this first. Okay, then going from here to here, and then once we got this work done, showing the net work done is like this. अरे बेटा वो डॉट प्रोडक्ट लिया ना, सी f dot ds, so that was the dot product of 6 I cap plus whatever 2y square j cap, but dot product with what? The displacement does not have x component, no, it is just dy j cap. Okay, so that's why it's becoming 2y square dy, no, this is for the path ap. Okay, this dot product here, don't forget the concept of dot product, na. Is it clear? No? Okay, so take this down quickly and do the calculation for the second path. Yes, both are same. So let's check this out. So what will happen in the second instance when we consider work done in path 2? So in path 2, what is happening is that first we are going along the y-axis. So we are going from the origin to this point here, let's say. So let's take this point here as B, which has coordinates 0, 1. So at any point in between over here, which is 0, y, so for OB, at a point 0, y is ranging between 0 and 1. The force only has a y component. It is 2y square j cap. Oh, sorry. Force has an x component also, because the force was 4 plus x, no? Like this. So this was the expression of force. So in this, when we put x equal to 0, it has a constant x component and a variable y component. So here, at any point like this, the force is 4 I cap plus 2y square j cap. But then the displacement is only along the y-axis. Okay. So at any point like this, you can see the force vector will be like this, but the displacement vector will be along the y-axis. So F dot ds, just 2y square dy. So work done from O to B is 2y square dy from y equal to 0 to y equal to 1. So that will come out to be your 2 by 3 joules, or 0.67 joules. Now similarly, when you're going from B to the final point P, so you'll be moving horizontally along the x-axis. This point is 2, 1. So at any in-between point, you'll see again the force will have both the components. So any in-between point here will have a fixed y coordinate of 1 and a variable x coordinate. Okay. So the force will be again a variable force, but the displacement will be this time along the x-axis. So for the displacement along BP at a general point x, 1, the force is 2 j cap, but the displacement is dxi cap. So work done, okay, so that will become plus 10 joules. So once again, you can see that net work done by path 2 is also 10.67 joules. Okay. So through this now we'll show that if we take any general path also, the work done will come out to be the same. But first make a note of this. Okay, so hope this part is clear to all of you. Now we'll see the interesting aspect that if we take any general path, so we can call it an arbitrary path. Arbitrary is like randomly chosen. Okay, from O to P. So let's say the path we are taking is like this, some arbitrary path like this. So any general point in between, so any general point where the particle is located at some coordinates x comma y, the force acting on it will have a general sort of direction. The displacement it will have, the differential displacement will have this kind of thing. Okay, so at x comma y, the force acting on it at that point is given by that relation 4 plus x I cap plus 2y square j cap. But this time the differential displacement will just be an arbitrary dx I cap plus dy j cap. It will have both components. Okay, so therefore work done, which is integration f dot ds from initial to final position here, will become dot product of these two. So dot product of these two is going to be 4 plus x into dx plus 2y square into dy. Okay. From the point O, so that is 0 comma 0 to the point P, which is 2 comma 1. So this work done we can separate into two integrals. Integration of 4 plus x dx, x coordinate changing from 0 to 2 plus 2y square dy, y coordinate changing from 0 to 1. Now, when you do this calculation, you can show that it is, first of all, it is independent of path, and it is always going to be 10.67 joules, independent of whatever path we take. So that shows over here that this force is conservative, because the work done is going to be independent of path. Any arbitrary or any randomly selected path also between the same 2 points will always give us the same work done. Okay. So hope through this example, the concept of conservative force is more clear to us. Okay. Okay. So this shows that work done is path independent. Okay. And that implies that this particular force is conservative in nature. Okay, so this is a very important aspect of the application of work energy, to understand the definition and the working principle for conservative forces. Now, the opposite of conservative is non-conservative. Okay, so let us look at the definition and examples of that. So, non-conservative forces. These are forces such that the work done actually depends on the path, or more importantly, the work done in a round trip should be non-zero. Okay. So, if the work done by a force is path dependent, okay, then it is defined to be non-conservative. and work done by a non-conservative force in a round trip is non-zero. Okay. So the most common example and the only physical example we have seen so far of non-conservative force is kinetic friction. Okay. For example, if we take a particle of mass m, okay, on a rough horizontal surface, okay, around a circular path, okay, of radius r, okay, on a full circle. Okay, so its angular displacement is 2 pi. Then the work done by the friction will be minus mu mg into 2 pi r. So you can see the work done in a round trip is not equal to 0. Okay, because what will be happening in this case is that if this is, let's say, our horizontal surface, and on this you're taking the particle on a round trip like this. So at any point of time, the displacement will be tangential and the kinetic friction acting on it will be like this. Okay, and opposite to the differential displacement at every point. So work done by friction, which is this dot product, will become minus mu mg into integration of ds in the round trip. So it will be minus mu mg into 2 pi r. Or any other kind of round trip you can see. Okay, you will see that the work done by friction, by kinetic friction, is a non-zero quantity even in a round trip. So by definition, it is becoming a non-conservative force. So as I told you, friction is our only physical example so far of all the forces we have seen, which is non-conservative in nature. Yes, Piyush, that concept is correct, and we will be looking at the operation of the curl at a later stage. We'll first understand the relationship between potential energy and force through the gradient operator. And at a later stage, we'll also talk about curl of a force being zero in case it is conservative. Yes, Samad, the integration of ds over a closed cycle, which is a circular path, is nothing but the circumference, which is 2 pi r. Okay, now suppose I take an example like this. Next, we have a force which has, it's a constant x component but variable y component, and the y component actually depends on the x coordinate. So it is like, let's say it is 2x j cap, where the force is in newtons, okay, and the x coordinate is in meters. So this is the force acting on a particle moving in the xy plane. Okay, so this time if the particle again moves from the origin to some point P. Now this time we'll take the point P as A comma A. Okay? And we'll take a more interesting example where our first path is like this. Okay. But our second path is the direct straight line. So this is path 1, and let's take the second path as the direct straight line like this. Okay. So calculate the work done by the force F for path 1 and for path 2. Let's try this out, people. Okay, so let's check out for each of the paths the work done. So for the first path, you'll see that if I label this point as E, let's say, okay, so work done from O to A. So for that, at any point like this, x comma 0, the force will be how much it will be having that constant x component and the variable y component. So 5 I cap plus 2x j cap, okay, and the displacement will be dx I cap. So at such a point, the force is like this and the displacement is like this, okay. So work done becomes 5 dx integrated from x equal to 0 to x equal to a. So that becomes plus 5a. Yeah, I'm not got correct answers for the second part yet, so I'll work it out and show you. Okay. Now for the work done from A to P, you can see that you are at a general point like this, which is at E comma Y. Your displacement is like this, okay, and your force is like this. So at a general point whose x coordinate is A but y coordinate is variable, the force has a constant x component as well as a constant y component. Okay. And this time your displacement is dyj cap. Okay. So your work done, sorry, 2a dy from y equal to 0 to y equal to a. So this becomes 2a square. Don't worry about the dimensionality. The 2 has a dimension of Newton per meter, whereas the 5 above has a dimension of just Newton. Okay, so this is also in joules, where A is in meters. This is also in joules. So the net work done in path 1, this is coming out to be 5a plus 2a square in joules. Okay, now let us look at the second path. Now the second path is a straight line where if you notice the equation of the straight line is y is equal to x. Okay, so when we are at any point over here, x comma y, that point has the same x coordinate and the y coordinate. Okay, so the path 2, it is along the straight line y equal to x. So when we see this path, any displacement vector ds like this is dx I cap plus dy j cap, where dy by dx is 1 because this angle is 45 degrees. Okay, so now at any point like this, we have some kind of a variable force F. which is like this. So the work done in the path 2 is this. So it becomes 5 dx plus 2x dy from 0 comma 0 to a comma a. So we will break this into two integrals, x going from 0 to a plus 2x dy, y going from, because the variable of integration in the second one is y now, because we are integrating with respect to y. Okay. Now what saves us is that we know the path. It is along the path y is equal to x. So we can replace x with y over here. So this is becoming this one. This one can be written as 2y dy. Okay, because of this. Okay. This is the work done in path 2. So you can see the work done in path 2 is not equal to the work done in path 1. So ultimately from this you will be able to see that the work done in the second path is not equal to the work done in the first path. Okay. So please make a note of this properly, and from that make sure you understand the final conclusion. So here work done is path dependent. So this is an example of a non-conservative force. Yes, Durgesh, I'll show for the first part. But first part was very similar to the last question we did, so expected that you should be able to do it. Anyway, so note down for the first part. Okay. Work done for path 1. Okay. Then we'll come back to path 2. Okay, so hope it is clear for the second path also. So for the second path, you have to understand that you are moving along the line y equal to x. Okay. So when you are at a general point x comma y, the x coordinate is the same as the y coordinate at that point. So for the second part of the integral, what we've written as 2x dy, now x can be replaced with y because particularly or on that line, where at every point the value of the y coordinate is equal to the x coordinate. If we'd been on some other line like y is equal to 5x, then we would replace x with y by 5, instead of y equal to x. Okay, people, so hope this calculation is fully clear. Okay. So this is how we check for conservative and non-conservative forces. Okay. Now let's look at a more general type of application. Okay, we'll come back to conservative and non-conservative forces again. When we discuss about potential energy also, this concept will become important. But let's come back to a more general application of the work kinetic energy theorem that we were discussing last week. So we have this situation now. We have this rough surface on which a body is being pushed by some kind of external force. So it's at an x coordinate of 1 meter initially, and by the time it comes here, let us say x is equal to 2 meters. Now initially its speed is 0. This surface has a coefficient of friction mu and acceleration due to gravity is like this. Now we are applying an external force on it, which is variable and horizontal in direction. So a variable horizontal external force given by F is equal to 10 root x, where x is in meters, F is in newtons, acts on the block moving along the x axis initially at rest at x equal to 1. Given that the mass of the block is 1 kilogram and the coefficient of friction is 0.4, make a free body diagram and show all forces acting on it. Find its speed v at x equal to 2 meters. So by the time it reaches here, it should have some speed v by using work kinetic energy theorem. B, using kinematics. Okay. So in the first part only, when you make the free body diagram, also find its acceleration A as a function of x, because the force is a function of x. So just try this question out, people. So basically in the first part, you have to make the free body diagram and equate F equal to ma, and from that you will get A as a function of x. Okay. The second part, in part A of the second part, you have to use the work kinetic energy theorem to show that the net work done is equal to the change in kinetic energy, and from that find the speed. Whereas second part you use kinematics, that is integrate the acceleration with the velocity. Okay, so let's understand the solution of this problem. Yes, Shikhar, that is correct. So when the body is at some general point x, there is this force acting on it, which is 10 root x. Okay, there is friction acting on it, which is mu mg. So that is 2 newtons, and there is mg and normal reaction. So it has a linear acceleration like this. So we have the equation F minus kinetic friction is equal to mass into acceleration. So 10 root x minus, sorry, the friction is 4, no, I think. Yeah, coefficient of friction is zero point 0.4, G will take as 10. So this is 4 is equal to mass, which is 1 kg into acceleration. So acceleration as a function of x is becoming like this: 10 root x minus 4 meters per second square, where x is in meters. So that's the first part. Okay. Now the second part, if we go by this, net work done will be work done by F plus work done by friction plus work done by mg plus work done by normal reaction. So work done by F will be integration F dot ds, which here will become F dx because it's one dimensional. So this will be from x equal to 1 to x equal to 2. So that is 10 root x dx from x equal to 1 to x equal to 2. So that becomes 10 into 2 by 3 x to the power 3 by 2, 1 to 2. So 20 by 3 into 2 root 2 minus 1. This is the work done by F in joules. You can see that this is approximately 20 by 3 into 2.8 minus 1. So approximately 12 joules. Work done by friction will be minus mu n into the change in x coordinate. So that will be minus 4 multiplied with 1. So work done by friction is minus 4 joules. Okay. And work done by weight and normal reaction will be 0. So net work done is approximately 8 joules. So that net work done should be change in kinetic energy. This because U was 0. So half into 1 kg into V square should be equal to 20 by 3 into 2 root 2 minus 1 minus 4, or approximately 8. So this is what we are getting by the work energy method. Kinetic energy is approximately 8 joules. The approximation has been done by taking root 2 as 1.4. Okay, so hope this calculation is clear. Now B part, you can also calculate the speed by using this relation. Acceleration was how much now? 10 root x minus 4. So this acceleration can be written as v dv by dx. So v dv, now integrate this from 0 to v and integrate this from x equal to 1 to x equal to 2. So you'll get the same thing. V square by 2 will become 10 into 2 by 3 x to the power 3 by 2 minus 4x. Same relation that you're getting below. No, we cannot use that because acceleration is not constant, na beta. Acceleration is variable. So how you can use the relation v square is equal to u square plus 2as. So whenever we have variable acceleration, we have to use integration. If the acceleration is known to us as a function of time, then we use this, that dv by dt is equal to a. If the acceleration is known to us as a function of x, then we use the relation v dv by dx is equal to the acceleration. So in this case, it's known to us as a function of x. Okay, people. So hope this solution is clear. So we'll continue with this tomorrow. Okay. So tomorrow we will discuss about potential energy and the relationship between conservative force or work done by conservative force and potential energy. So try out few questions from H.C. Verma and also read about potential energy and prepare for tomorrow's lecture. That's it for today. Thank you people for attending.